In Lesson 90, Paul demonstrated that state machine programs can sometimes run so fast that we can't interpret what they're doing. He introduced us to the no-op instruction and the delay modifier, both of which can help us to slow down the execution of our program by throwing cycles away. He also explained conditional jumping, which lets us implement a form of for loop or while loop functionality in our assembler programs. And finally, Paul demonstrated bit shifting as a way to do rudimentary math. Our Lesson 90 assignment was to create a 4-bit up counter entirely in a state machine. The main MicroPython while true loop should be empty. Also, the up counter should run as slowly as possible. This will require us to use the lowest possible program frequency and to create a delay in the program by putting a series of no-op delay modifier combinations in a long as possible repeating loop. Another challenge of this assignment is that the Pico W state machine assembler does not have an add command or a plus operator. It does, however, have the ability to invert a binary number and to decrement the contents of a register. So the question is, how do we implement addition by decrementing and inverting? Consider the traditional addition shown here. Now consider this subtraction. We invert the original number and then subtract 1 rather than adding 1. We invert the answer and we get the answer we would have got if we had simply added. So inverting, subtracting, and inverting again seems equivalent to adding. Let's have a look at the code. As usual, we start with imports. We import pin because we use the pin statement in the PIO instantiation. We import RP2 because we're going to be programming a state machine. The RP2 decorator on line 7 specifies that we'll be using out instead of set. We'll be starting by resetting our 4 outputs low, and we're setting the shift direction parameter to right. The up counter function, which starts on line 9, contains the assembler code for our assignment. The code will be downloaded to state machine 0 when the MicroPython program runs. The wrap target label signals the beginning of the state machine program. The program holds the accumulated count in the X register and will start counting from 0. So we set the X register to the inverse of 0, or 1111 in binary. The show count label is followed by a move instruction which copies the inverse of the X register to the LEDs. After displaying the current count on the LEDs, the set statement on line 14 sets the Y register to a count of 31. The delay loop label is followed by 24 no-op instructions, each of which includes a 31 cycle delay and therefore consumes 32 clock cycles. That's a total of 768 cycles. The jump if non-zero command at line 40 will jump to delay loop until the Y register contains 0. Each time this instruction jumps, it also decrements the Y register. It will use up another 32 cycles. So the program will repeat lines 15 to 40 32 times. In total, this loop will cause a delay of 768 plus 32 times 32 times through the loop, or 25,600 clock cycles. Our 0.5 millisecond clock period makes that a total loop delay of 12.8 seconds. When the Y register reaches 0, program execution falls through line 41. This command will jump to the show count label and decrement the X register until the X register equals 0. Decrementing the X register combined with the two inverse operations at lines 11 and 13 results in the addition functionality we're looking for. Once the X register equals 0, execution falls through to line 42, at which point we jump back to wrap target and do it all again. Line 45 is the instantiation of the state machine. It specifies that we'll load the program on state machine 0. The program can be found in the up counter function. The operating frequency is 2 kilohertz, and GPIO pin 12 is the first pin in our scope. Line 51 activates the program in state machine 0, And in the usual try except clause, we can see that the while true loop is empty, and that if the user presses Control-C, state machine 0 will be deactivated and the user will be advised that the program has stopped. Here's how it looks. Once this homework was complete, I watched Paul's lesson 91. Watch it if you haven't. There's a link in the description. Highly recommended. Paul's brilliant hardware change alone is worth the visit. But there's more. As it turns out, 31 is the maximum value you can set into the Y register, but you can use the IN command and the ISR to shift much larger values into the Y register. I could have had a much longer delay with many fewer no-op statements. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.